Data Voyagers.
Machine learning isn't science fiction anymore. It's not locked away in research labs or reversed for Silicon Valley's elites. It's shaping the ads we see, the music we stream, the fraud alerts on our credit cards, and even the way billion-dollar companies make decisions. But here's the question: do we really know how it works? Welcome to the Data Voyagers podcast, navigating the story behind the numbers. I am Igor Alcantara. Oi, pessoal. And today's episode is about machine learning. No, it's not the race against the machine learning, it's more the rise of the machine. And as always, I have here with me my friend, fellow Click ambassador, and co host of this podcast, Angelika Klidas. Hi, Angelika. My machine learning module predicted that you will be here today, so I think you got it right. Thank you. Hello.
Hoi, Igor. En hoi allemaal, fijn dat jullie er weer zijn.
I have no idea what you said, but I know it's something very nice. I need to, yeah, I need to stop my Czech learning and switch to Dutch. Uh, okay, so today we're talking about this excellent topic. If you think you know machine learning, I'll ask you to trust us and listen to this episode anyway. There is probably something new that we'll discuss today. And since I'm asking, um, since I'm in the asking business, actually, let me ask something else. Subscribe to the Data Voyagers podcast. And while you are in your favorite podcast application, Spotify, Apple Podcasts, Overcast, any application, no, just give us 5 stars. We passed the 100 stars on Spotify, but how about we try to get to 200? So give us 5 stars. Follow us on LinkedIn, ours personally, and also the Data Voyages page. All of the links are in the post of this episode. We can check it in your podcast app and visit our website and online store. So if you go to datavoyagers.net, you can buy products. They're super nice, and you can help support these podcasts and support us in any way you can, like share the episodes, like, comment, suggest to your friends and colleagues. And talking about support, let's hear a quick word from our sponsor, IPC Global. At IPC Global, we believe artificial intelligence and machine learning should be more than buzzwords. They should deliver real value to your business. That's why we partner with Click, the leading data analytics platform, to help organizations to put AI to work. From predictive modeling with Click Predict to AI power RAG and insight with Click Answers, our team brings the expertise to guide you from strategy to implementation. Whether it's spotting trends, reducing risk, or unlocking new opportunities in your data, IPC Global helps you make AI and machine learning practical, actionable, and trusted. To learn more, visit us at ipc-global.com and discover how we can help your organization turn data into decisions. Let's dive in. And let's start, Angelika, with the question: what is machine learning?
Well, um, when people hear the words machine learning, or they often think something it's very futuristic, like the amazing movies that we ever saw with Arnold Schwarzenegger. I'll be back. Making robots that they can think for themselves, have emotions, and so on, or a computer that suddenly wakes up and starts making decisions like a human. But machine learning is actually more simpler, and at the same time, it's more powerful than that. At its core, machine learning is about teaching computers to learn patterns from data. Instead of explicitly programming every single rule like we do in a CRM system, like if X happens, then do Y, we give the computer examples. and the computer figures out the rules on its own. And here's an analogy. Think about how a child learns how to recognize animals or a certain type of blocks. You don't hand them a 1,000-page rule book on what makes a dog, or a block, a round block. You show them pictures. And when we continue with the dog analogy, you point out a Labrador to your child and you say, "That's a dog." And you point out a Chihuahua and you say, "That's also a dog." And eventually, after enough examples, the child starts to see patterns. They see floppy ears, they see four legs, they see a waving tail, and yep, they think that's a dog. That is what mommy or daddy have taught me. And machine learning works the same way, but instead of children, we're training them with algorithms. Now, and why is this different from traditional programming? In traditional programming, humans define the logic, and in machine learning, the logic emerges from the data that we're feeding it. And that means the more data you feed it, the better it gets. And the outcome is as good as the data it's fed with, right? That's also what is important. And sometimes in ways that surprise even the people who build it when the outcome is that good. And here's directly the key distinction. Machine learning is a subset of artificial intelligence. Artificial intelligence is an umbrella term, right? And under it, you have the different approaches, and machine learning is one of the most important. And I think also, Igor, the most used. Um, and it's how we build the systems that get smarter with experience. And then there's deep learning, another subset which uses all kinds of neural networks and massive data sets to reach new levels of accuracy. Um, but guys, machine learning is not magic. It doesn't think like we do. It's not creative and it doesn't have any intuition. What it does, it recognizes patterns in data and use those patterns to make decisions. And when you think in that way, it starts to make sense why machine learning has become so central to our modern lives that we have nowadays. Every time when Netflix recommends you a next show, or every time your email filters out spam, or every time you listen to a favorite podcast like the Data Voyagers podcast on Spotify, or every time your credit card company flags a suspicious transaction, that is actually learning at work. So when we say machine learning, we're not talking about the same abstract, futuristic technology. No, no, no. We are talking about the everyday practical systems that quietly shape decisions all around us. And today we're going to break it down how it works and how you can actually use it in your own world. And now, Igor, I believe you are going to guide us into the world of the machine learning concepts, like learning under supervision and without supervision.
Exactly. So let's talk about some core machine learning concepts. And but before I start, I just wanted to point out something to our listeners. I've been writing some articles in our blog, the Data Voyages blog. So if you go datavoyages.net, you can find those. So I've been writing some articles that basically each article, I take one concept in machine learning and I break it down in a very simple, fun language. So it's designed to everyone. So no words, there's no math or anything like that. It's not like other articles that are too technical. That's not the idea. It's that you actually understand. So I'm writing a series of articles, and once this episode is published, I published the eighth article. So there are eight different articles. So if you want to know in more details, I'll summarize here. But if you want to know in more details, you can go to datavoyages.net and take a look at it. So we talk about SHAP statistics. What is the machine learning pre-processing of data? How Click Predict actually does it. How we measure performance, which is something we'll discuss here, but it's way more detail there. Well, there was one about data drifting. There was one about time series. There is one about the curse of dimensionality. There was one about the algorithms of regression. And another one that is not live when we are recording, but will be live when this episode is it's public. Another one about the algorithms of classification. It's all click predict centric, so it's like it's how click predict does it, but it's click predict uses industry standards. So you're not learning just about click predict, you're also learning about machine learning in general. So let's dig into some core concepts. Um, everything that you work with, even if there's a machine or a software that is doing most of the work for us, if you understand a little bit the concepts, you actually can identify problems, or you can anticipate areas of concern, or you can actually understand what is going on. And the first concept that I want to bring up is there are different types of machine learning, and there are many ways we can classify machine learning. The one that we chose for this episode is based on how the modules learn or perform the task. So we have basically two categories of machine learning. We have supervised learning and unsupervised learning. And when I say supervised and unsupervised learning, I'm not talking about kids when Angelika and I grew up. At least I grew up in Brazil. There was no parenting. We basically were like wild creatures, like running in from school to the streets. Different than today. So was very unsupervised. It's a miracle that I'm still alive. Different than today, which is very, very much supervised. Like we have apps and we have tracking devices in our kids and all of that. So it's very different. But that's not what I'm talking about. When I say supervise, then you might ask, okay, who's supervising? Is it a human? No, it's a data. The data is a supervisor. What it means is that we take data from the past where we already know what happened. We already know the answer to train the machine learning model. So imagine you teaching a module to detect spam emails. So you feed it thousands of examples of emails that already have the label if it is a spam or not a spam. Let's call it spam and ham. So the model learns from those examples, and the next time a new email comes in, based on what it learned, it can predict which category it belongs to, spam or ham. So we call this supervised because those labels, spam or ham, spam or not spam, are the teacher in the supervising process. So the key here is learning. So it learns based on what happens in the past. You don't need to give the rules. So it's not a set of if else statements. Oh, if it has these specific words, have like uppercase or this or that. If it comes from an email address that you didn't receive as often, you don't have to come up with those rules because, spammers and scammers and hackers, they come up with new strategies every day. So there's no way you can provide every single rule. People will find a leak in your rules to get the spams pass in. It's not how it works. You give the data and the answer, say look, and then the module will come back and say, when these conditions happen, then this is what the result, the target, like it was a spam. When this condition happened, then it was not a spam, and so on. So the interesting thing is the main task is to make a prediction, right? The main task of machine learning, supervised machine learning, is to make a prediction. But there is a side effect, and sometimes the side effect becomes the real feature. Like, for example, when microwave oven, when people invented the microwave oven, it was in 1940s, 1950s. They were actually researching radar systems, like means of communicating radar signals. But then the researcher was doing the research and has like a bar of chocolate in his pocket. And he realized that it melted. He said, oh, interesting. Maybe I can use this to heat my food. And then we have microwave. Viagra is another one. Viagra was developed for chest pain. angina. And then the guys, when the patients, like in the trials, were reporting the side effects, they said, "Oh, interesting. We can make Pfizer realize we can make more money with the side effect than the actual main feature." So, how is this related to? How is that related to machine learning? Well, the main task is to make a prediction, but the side effect, I think, is more interesting. The side effect is in order to learn from the past data, it has to understand all of the relationships one column has to another and how they work together. Basically, it has to learn the businesses, mathematically speaking. So the side effect, which is understanding why something happens, it's more important than actually what will happen. Because if I know what will happen, but I don't know why, there's nothing I can do. But if I know why, that's very powerful. So that's supervised learning. Now, unsupervised learning, like myself when I was younger, is different. So there are no labels, there is no past data. You just give the module the data and ask it to find patterns on its own. Actually, it sounds a lot like how I was raised. I mean, kids in the 1980s, 1990s was just wild creatures. Anyway, um, think of it like you drop a group of people into a room without name tags, without anything. They don't know each other, and just observe and ask yourself who naturally clusters together. So, and then you try to develop an algorithm to predict that. So, the algorithm might notice that some people are wearing business suits, some are in casual clothes, some are holding coffee cups, some are taller, some are shorter, some are male, some are female. Um, so, it will people will group them based on whatever they feel like it. And if we have an algorithm that will kind of clustering them, we actually will observe there was not necessarily a prediction. When you say unsupervised, not a prediction, it's more like a classification and observation. So then we look like and say, yeah, like you naturally see there are different groups of people, like clusters. Um, and that's an unsupervised. We didn't have to train an algorithm to preview with the previous data. It will naturally happen. So you use the data to understand the data and organize the data. Another important concept is also the difference between, and these are two supervised machine learning, the difference between a classification and a regression. That's another way to classify machine learning. It's so first we saw these let's say level one types: supervised, unsupervised. Now let's get supervised and let's analyze deeper. And then in supervised learning, the main two, I mean, there are more than that, but the main two types of machine learning are classification and regression. Classification is about putting things into categories like spam, not spam, dogs and cats, churn, not churn, patient readmitted, patient not readmitted, patient survived, patient did not survive, things like that. Regression is about predicting a number. And in my article about regression, I explain why it's called a regression. But anyway, actually, that article is funny because I'm talking about my youth, and there is a picture, a real picture of myself in my early 20s. I think it was like 2021.
I think the latest article, right? On the latest
The
article where you were in a band.
Yes, the later
Yeah.
article where now that we're recording, but when this is becomes live, there will be another one after that that's written, and then I'll just doing a final review. But yes, the one about regression, I was in the band. Yes. So, so regression is predicting numbers. It's not like regretting something that you did. So, for example, how much will sales be next quarter? What is the expected price of this house? So, both of these classification regression are types of supervised learning, but they of course answer different types of questions. Now, another concept is the difference between features and labels, or features and targets. It's kind of same thing. So think of features as the inputs, the pieces of data we use to make the predictions. And the labels or targets are the outputs, the answers we want the model to predict. So, for example, if you're predicting house prices, features might be number of bedrooms, square footage, location, if there was a renovation or not. So, those would be the features. And the label or target is the actual sales price, is what you predicting. One more thing that is often get people surprised is that machine learning is really just math wrapped in data. It's just math. So when you strip it down, it's about finding the best mathematical function that maps inputs to outputs. That's it. It's a mapping process using math, which is math like is the greatest shortcut created by science.
Yeah,
Or
what I
discovered
always
by
try
science.
to what I always try to explain to the public that listen to my AI awareness training, or is what an algorithm is. And an algorithm is something that you put in, you have a process of handling it, and you have an output.
Yep, that's it. That's it.
That's it.
Um,
Just like
and
as humans do, right?
Exactly, exactly. So there's no wizard doing magic. So it's
No.
no magic, as you said. When you open the curtain, it's just about algorithms. And now there's also the term algorithm. What is an algorithm? What is a model? Because sometimes you call it an algorithm, sometimes you call it a model. What is the difference? The classic example, I think, is the perfect one that people use to explain this. Is it's about cooking. An algorithm is a recipe. You get a recipes book and you have different algorithms. Let's say, oh, I have chicken and I have cheese and I have whatever pasta. What can I do with these? There are many different recipes, many different algorithms. The model is the actual meal, because I can take one recipe and you can take the exact same recipe, and we might have different models. Might have different dishes, because we cook a little different. One might put a little bit more salt on more, or maybe the ingredients are different. So that's the difference between algorithms and module. So when you say a module is a trained algorithm, in other words. Um, Now, when I create a module, I want to make sure the module is able to generalize. In other words, it has to work with new data that comes in every day. So then we hit another two pitfalls on two important concepts: overfeeding and underfeeding. Both are bad, by the way. Overfeeding is when the module memorizes the training data so perfectly well that it fails to perform well on new data. So it's that, and I've seen this so many times, so many times. I get really upset when I hear people saying, it's usually salespeople who has very little knowledge of what actually happens, because they don't read the Data Voyagers blog or listen to the Data Voyagers podcast, or they don't have that kind of knowledge. And they say, yeah, you use this auto machine learning tool like Click Predict, you don't need data scientists. You can fire all your data scientists. And I'm saying this is wrong, not because I'm a data scientist, but because I'm seeing this so many times. You get this person, um, all the great intentions, and the person gets and uses Click Predict or whatever tool they're using. And in training said, oh yeah, you're right. I don't need a data scientist. I got a 99% accuracy in my training module. Great. Congratulations. You just overfeed it. Your module is pretty good in training. But then once you get getting new data that was never exposed before, it sucks. I was trying to find another word. It's terrible. It's like a student that memorizes the practice test, but it fails the real exam. Really classic. You do the qualification exam. You think you're ready for the certification. You go to certification. There are different questions, same topic, but different questions. And then you
Okay.
fail miserably. So
Yeah.
that's
Let's
overfeeding.
grab a little bit back to this problem, because I
Mhm.
really would love to understand this one, and I think the public needs to understand this problem.
Mhm.
overfitting and underfitting.
Yeah.
So you say that overfitting actually happens when the data is too perfect.
Not the data too perfect, the model is too perfect.
The model is too perfect. Okay.
Yes. You
And
train the model, you see the accuracy, oh my God, it's almost 100%. Sometimes it is 100%. And
mhm,
then you overfeed it. Your model basically learned the training, but it didn't learn the rules of the game. It didn't just learn that.
okay. And
Yeah.
then underfitting is that it's approached the model approaches the data too simple.
Yes, then it means that the assumption that the models made are too simple. So then the model do not capture like the actual patterns. It's like, for example, you try to fit a straight line through a set of data points that are
Mhm.
curving. It's not actually a line. So those are two problems. So the BAS is something in between. Is the fitting? It's not the over or under. Is the fitting? Is actually you actually learn the rules of the game. So then when new data comes in, you can apply them successfully.
Okay.
And
It's
finally,
very difficult, huh?
yeah, I mean, I study like years. I study years,
Yeah.
and yeah, I mean, I went to college and master degrees and specialization and training and experience and all of that. But yeah, it is the game. It is the game.
Can I ask one more question about it? How can you overcome overfitting or underfitting? How can as just somebody who is on track, he's learning to become a data scientist or a very advanced analyst, data analyst. How can he or she overcome or avoid overfitting and underfitting?
Well, you need to understand the problem you're trying to, or the question you're trying to answer. You need to understand that. You need to understand the business. That's, I mean, it's a very. We could do an entire episode on that.
Another
But
topic. Okay.
but it's good. But it's actually it's a great question. So you need to understand the game. And let me explain a little bit better. I'll give you an example. Um, it was a very complex problem that it was before Click had Click Predict. I did everything like manually in R. Like actually had to write all of the code. So there was like many years ago. Um, and we had a customer that they were trying to, it's a utility company, electricity company, and they were trying to, what they wanted to predict is if there will be electrical outages in particular regions in the city. It was specifically in situations of like big storms, because in without big storms, there's basically no outage. You know, the system was pretty stable. So we had to predict that. Um, Initial approach was like, yeah, let's get the data we have. We have the weather data. We have like transformers data, the regions. We have there was a lot of data. 10 years of data was so much data. But then eventually we actually and then we trained the model. It was very complex. We trained multiple models, but we were underfitting. We were not able to capture because we're considering there was a problem with the weather data because weather data from the past is what happens, while the data from the future is the weather data prediction. So you adding which is has a huge margin of error. So if you using something that has some error to make a prediction, so there's a data quality problem. Uh, but the main reason was we did not have the most important data set. The model doesn't know what it doesn't know. The model doesn't know the data that you do not provide. So then we had to do a research and understand, okay, what are the main causes of electrical outages? When electricity is out in a storm, what are the main causes? Then talking to people, oh, it's like lightning, the hit trees or the hit infrastructure, and then that happens. So then we got lightning data on top of the weather data. But the problem with that, we had particular regions with big buildings where we have more data than other regions. Then the model overfeed it because it kind of It was able to predict on those areas, but not in other areas. So we were from under to over. Then we've realized, well, we need vegetation data. We need to know where the trees are. So we need to know the density of trees in each area in order to make the prediction. And then we went from overfitting to actually fitting. So that's I think that's a good example. It's a very complex example. It was possibly the most complex machine learning I ever done it. Also because I had to program everything. But it kind of shows like the differences. So the key part is you have to understand the businesses.
Yeah.
Another thing is you need to understand when the prediction it's made, when the prediction is made, and you can only provide the data that is available at that time. So let's say I'm predicting if I'll give you a very stupid example that is obviously wrong, but just to illustrate, I'm trying to predict if a patient will return to the hospital within 30 days or not, the classic patient readmission. And then as part of my data set, when I trained, I already know if the patient returns. So I have like I don't know, date of return. I cannot provide date of return or reason for returning or something like that to my training module. Because when I need to make the prediction, the I don't have that information because I don't know yet. So let's say I have to make, when do I need to make a prediction? Let's say, oh, it's one day before the patient leaves the hospital. It's while the patient is already in the hospital. So that's what I need to provide the data. So I need to exclude everything from the future of that data point to the data module, to the data model I'm using to train the module. So then I don't leak information from the future when in the real case. So that's another thing.
That was an example of overfitting where you train the model that precise so that it performs very well on the data that you feeding it with, but it will not respond good in predictions on new data that is entering. That's the overfitting part, right?
Yeah, because it basically learned the past, but it doesn't know how to predict the
Exactly.
future. Yeah.
And the other one that you explaining was that's the underfitting, is that
Yeah.
when the model has not learned enough from the data, so it
Yeah.
performs badly on the training as well as on the new data.
Yeah.
Did I
Sometimes, a
understand
lot
it
of
correctly?
times, exactly. You understand perfectly. Sometimes for underfitting, it most of the time is you do not have enough data,
Hmm.
either rows, either columns. You don't have the data. So, and sometimes not even enough data. You don't have the right data. You don't have the data that actually impacts the output.
Hmm.
It's like predicting if an employee will leave the company or not, and not provide information like salary.
Hmm. Yeah, and then
Well,
some, and also
yeah,
the
because
risk of
money is a big motivator for people
yeah,
leave a job or not. So you have to provide it.
yeah, and then you have, if you have the columns, you have to take care of the curse of the dimensions, right? So the
Yes,
more columns, it
too
makes
many
it too many
columns.
columns,
Too many
makes it
columns
also
is also
difficult.
bad. Too many
Is
columns is
that
also bad.
is that then related to overfitting or underfitting, or is that something else?
The curse of dimensionality is related to both.
To both. Oh, interesting.
So yeah, too
Okay.
many columns can underfeed the model or can
Mhm.
overfeed the model. And in order to understand that, we need to go to the next concept, which is bias and variance.
Thank you.
So bias is when your model makes strong assumptions but misses important details. And variance is when it gets distracted by the noise in the data.
Many.
So you need
Yeah.
to balance. So they are kind of two opposite sides of the spectrum. So balancing these two is one of the hardest part of building a reliable machine learning model. And just be clear, now that we have tools like Click Predict, the programming piece, we don't need to do it. The programming piece of the machine learning and programming piece of the pre-processing the data and evaluating performance, all of that, we don't need to write Python R code for those anymore. We have tools like this. So the data science will work more as a scientist and analyst role. But we do have the work of preparing and curating the data true machine learning.
Yeah.
And we can use tools like table recipe, data flow, that really helps that, so we can do a no code approach for that. But you need to understand the businesses. That's
Yeah.
how actually you differentiate yourself from like the AI, and also how you actually bring value. So you need to understand the business. You need to understand what you're predicting. Sometimes visiting a customer, let's say it's manufacturing, visiting the plant and see how they manufacture stuff, how they package it, how they store it, how they ship. Then you understand, oh yes. And then you realize the kind of data that you don't even have it sometimes, and you need to collect it. That's very important. But let's bring it to bias and variance.
Yeah.
So um, one second.
So should we do a recap of the section?
Oh, actually, no.
Supervised?
Let me.
No, there is more. Wow.
No, yeah. Um, I'll get you. I'll get you a question. But let's. So there is the difference. So sometimes bias is when, and I think we'll discuss this in a little more detail. But bias sometimes is when you have parts of your data that are underrepresented or overrepresented. So that's when a data is biased. So then you're pretty good at predicting one thing, but pretty bad at predicting the other things. So overall, the model is bad. And variance is sometimes the data is there's so much variance that sometimes there's so much exception rows that the the module becomes too focused on the exceptions. That only happens once in a while, and thinks the exception are actually the rule. So then you also doing that, you also have a bad module. So once we understand these basics, then the machine learning stops feeling like a black box. You start to see it for what it is a structured way to learning patterns from data with strengths and weaknesses that depends on how we use it.
Yeah, and I think I wanted to ask you a question about it, but I think you answered it already about biased data, right? Because if I understand it correctly, biased data is that when some values are overrepresented and others are not represented, or the
Yeah,
other way around, right? Important details.
yeah. So let me explain this in more detail. So when we train a machine learning model, um, the data we have, it's a mix of two things. Let's say you've seen like a trend or something. So it mix of two things. It's a mix of signal. The signal is the real underlying pattern, that the
Yeah.
actual what matters, and the noise. The noise is random fluctuations, errors, or irrelevant details. Like one day, a patient that should not be returned, something happened. The patient got ran by a car and returned to the hospital. There's no way you could predict that. But then let's say there was an accident with the bus, and a lot of patients returned, and coincidentally they were coming from the hospital to, I don't know, whatever they lived, and they were all in the same bus, and it happened. So what is the chance that that happens? Well, one in a billion, I don't know. It's very rare, but it happened. And then you have, if you have that exception in your data, it might, it's a noise, and it might compromise your model. So a machine learning bias happens when a model consistently misses the true underlying patterns, and it can happen for two main reasons. One is unbalanced data. It's when some groups or patterns are under or over represented in the module. Um, like there are some the first modules for face recognition were highly unbalanced because they were trained in Asian and white people only, mostly male. So they were
Reminds me of this book.
incapable. Yeah, yeah. Oh,
Yeah,
that's a very
that's
there
a
is a very
very
interesting
good
book. Yeah,
book. Yeah, Unmasking AI. Yeah.
yeah. So um, The problem with those models was that when a like a person that was not white or Asian male was trying to use face recognition, it didn't work. So it was always was also it was extremely biased. So that's one example. Another example, there were some machine learning models in the past that were trying to predict crime, but because they use specific data sets, they were basically flagging every person, like every black male, as guilty of some kind of crime. So extremely hate racist. But anyway, that's a separate conversation. That might be an interesting episode for the future. The racist AIs, which actually there's a lot. I mean, the AI is not racist. The data
It's racist.
represent a racial bias
Issues,
structure, and
bias. Yeah,
then the machine learning learns from that data.
exactly.
So the two ways we can get data bias is by unbalanced data. The other is noise in the data, like random fluctuations, error, irrelevant details. If they are overrepresented, they can distract the module from the real signal. The example of with the bus is one example. So for both situations, we lead to the same outcome. The model misses what is actually important. So let me give you an example. Let's say you have a model trained to detect pneumonia from chest x-rays. So we have chest x-rays for a lot of patients, and basically it's a classification problem. You want to detect if people are healthy, if they have a bacterial pneumonia, if they have a viral pneumonia. Actually, this I was working in a project like that for a nonprofit in Brazil right at the beginning of COVID, before they have tests to test if someone had COVID or not. So we're trying to predict was pneumonia, other conditions, healthy, or COVID from X-rays. And I have a list. I have a collection of something around 5,000 X-rays that I had to come in and labeled, and then we're able to train them out. It was pretty good, but we only used for 1 month because then tests came were cheaper. But let's say you have that to predict, to identify, diagnose someone has pneumonia or not. But let's say most of the images you have come from older patients. Your model may perform poorly when the patient in the real data, in the new data, are children, for example, because their cases are underrepresented in the data. So that's the imbalanced data. Or maybe you only train the module using sick patients' images. So when someone healthy comes
Yeah,
up, you cannot identify them. Now, about noise, let's say if the x-ray images comes with the hospital name or the hospital logo, so then the module might accidentally learn to recognize that logo and scan and when you use that in another hospital, is not able to perform because it didn't find the logo, those images, and misdiagnosed. So that's another thing that we need to take into consideration. Um, and so the module will, in all scenarios, it will fail to capture the true signal, if what is the diagnosis, and will become biased. Um, so that's, I think, that
yeah.
explains.
It would. It's very. So the things that we discussed in this section are very actually mega important. Oversizing, undersizing, bias, noise. Um, I'm wondering if there will be some kind of solution in the future that gives us a warning, a heads up when this occurs. That would be so cool.
Actually, the future already
It's already here.
arrived, is already here.
Okay.
So we do have a bias. It can be calculated. Actually, I'm already planning an article about bias. So there'll be the ninth article, maybe 9 or 10th. I'm in between this and another topic that I'm not going to give any spoilers. But anyway, but in Click Predict, for the people who use Click, in Click Predict, bias uh, detection. It's not detection, the term they use, but it's something around that line, like bias detection or alert. um, it will be part of the it will be part of the next release, not the exact next release, I don't think, but
It's
will be
somewhere in the
available
near
soon,
future. Somewhere in the near
very near future,
future.
because it's
All
already in the
right.
roadmap. Yeah, I just don't have the date. So yeah,
That's
so
super
that will be.
interesting, right? That's super
And
interesting
mathematics,
because
and it's statistically, it's kind of if you, it's kind of not complicated. Let's say, let's take gender for example, and let's say you have just like the basic, like male female gender, and then you have a
mm,
data set that 80% is male. You already know it's biased.
yeah,
So if you see like the proportion, and especially if a column, if a feature, it's very important to the prediction of the model. It
mhm.
has a higher Sharpe statistic, and it's unbalanced, then you probably have a biased data set.
Super interesting. Really super
Yep.
interesting. But I think we should go to the next section, and that is about the actual workflow of machine learning, right? Because it begins with a business question and it ends up with something amazing in predictions, machine learning solutions, and so on. So actually, it's the step-by-step process that takes us from the raw data actually to meaningful predictions. So the first step that we should think of as I'm the business girl, right? From the two of us, you are my data scientist, my hero, my data hero. I am only a business analyst who loves to work with the business and define problems, right? And my suggestions, I just give them hopefully well worked out what I want to my data scientist. So defining the problem, I think, is very, very important. And there, I think uh, I know, I read about it, that a lot of projects fail because they don't know what they want. They didn't define the problem. Um, you need to come up with the problem, defining it, and from there grow. So you need to understand: are we predicting customer churn? Are we forecasting sales for the next quarter? Are we going to detect fraudulent transactions, or are we just in my former projects, what I did at a company here in the Netherlands where we had to predict for emergency GP posts, right? They are only open in the evenings and during the weekends and festival days. And they wanted to know, based on the historical figures, how many patients will come to our GP post in the emergency post. And by all means, we want to see if the prediction about population growth in in the area in the region, or the decrease of the population, or even the weather conditions and so on. And we found out a lot of interesting things in when we defined the problem and actually solved the solution. But later about that too in this section. So the key message here is that you can clearly define the question, but no algorithm in the world is going to give you a useful answer. So this is why it is mega important to define the problem. And once you know the problem, the next step is that you have to collect and prepare the data. And let me tell you, this is usually the hardest part and the most time consuming part. Find that data and prep it. And data is messy. It's missing values. It's inconsistent formats. It has outliers that do not make any sense. And before the model even sees the data, we have to clean it, you have to normalize it, and sometimes even engineer new features that better represent the problem that you want to solve. So for example, instead of just giving the model a customer's raw transaction history, we might create a feature that represents the average purchase last quarter. And that gives the model something more meaningful to learn from. So from defining a problem and finding your business case at the end, uh, collecting and preparing your data, you have to prepare the data, as we just explained, and then you have to split it into training and testing sets. And the training set is what the models learns from. So the test set here is what we use later to evaluate how well it generalizes to data and hasn't seen before. And sometimes we even use a third slide in our approach, and that's a validation set, right? To fine tune the model while keeping the test set untouched. So Igor, I know it's here super important to know that our algorithms learn from the past, right? Do you know by any chance if it's possible to use synthetic data, the fake data, for example, you prepared with a generative AI solution, and why would you do so? Because I heard something about synthetic data and using it.
Yes, I have used it. Synthetic. I use synthetic data a lot, but not to real problems, real implementation. I use a lot for demo reasons, but we can use for a real example. So, as you said, yeah, algorithms can learn from the past, which means the quality depends on what we give to them. So it is possible to use synthetic data created with Gen AI or something like that. And let's go the pros, and then I'll talk about the risks. So some good reasons is like sometimes you want to balance data sets, because sometimes groups or cases are underrepresented and you don't have the data to better represent them. Like, for example, fraud cases. Fraud, in most cases, they are rare. So you have in every 1,000 transactions. This is not a real number, by the way. Don't quote me on that. Just an estimation. That basically the voices in my head are telling me. But let's say fraud cases. In each 1,000, you may have two or three. I don't know how many, 10. So it's very small. So if you want to understand how they work better, you need to produce more of those. So you might create synthetic data, or sometimes rare conditions. So, and there is a problem with rare conditions, and which I will discuss in a few minutes. But rare conditions is very difficult to predict as well. So you might want to use synthetic data for that, or sometimes easier scenario to protect privacy. So you don't want to expose the real records, so then you create synthetic data based on the real records. So then you don't expose the real records. Or to do simulations on rare and extreme scenarios. So then you don't actually do the uh, unethical experiment of making those rare conditions. You create synthetic data, create simulated scenarios, and then run the modules to predict those, to see how that happens. Sometimes just to increase the data set when it's too small, there's too little data available. So there's all, of course, it's not any synthetic data, it's not random synthetic data. The synthetic data needs to respect the statistical properties, the John-Tucky properties of the data. So let's say you have a data that is a salary. So the synthetic data needs to have the same average or the mean, the same standard distribution. Um, I'm sorry, the variance, and then it has to be in the same range and the kind of stuff. And also based on the category, it's not blindly based on the role, based on the department. It will respect each one of those properties. So otherwise you go to the Simpsons paradox, which might be an interesting episode for the future. So there's a bunch of rules statistically that you need to follow to create a synthetic data. But it's based on the statistics, it's based on expected values, it's based on properties, it's not real. So synthetic data does not replace real data. It can extend it. It can make models more robust, more fair. But the risk is that the synthetic data is poorly generated, or unexpected things happen. The model might learn patterns that do not exist in reality. Or if you overrepresent a condition that is rare, then you add in noise. So that's the
Yeah,
other. So it
exactly.
has a balance. Oh, it's a rare
Yeah,
condition. It happens only 1% of the patients. You might want to generate synthetic data to have more rows, but not in order to make that representing 50% of the data, because then you're not making that rare condition common, which is not the
exactly.
case. So
Yeah,
you're adding noise. So it's a fine tuning balance. That's why you require a teamwork, like the data scientists in the business. Like I'm using like healthcare examples because I went to medical school. I work a lot with these kind of cases. Manufacturing, education, and healthcare are the three main areas that I work. But so in that case, you might want to work with the physician, the doctors who work that treat those kind of diseases. They will tell you, okay, that might happen, that
They
might
know
not
their
happen.
business.
Yeah, they know
Yeah,
their
they know
businesses.
their
I
business.
hope they
Yeah.
do, because they're charging a lot of money for that.
Exactly. Yeah. Yeah. The system in America and here is completely different, of course. Uh, but then healthcare is healthcare in this case. So we discussed defining the problem, finding that data set, right? Preparing it. What was the other topic that we discussed? Collecting, preparing, and we
Hmm.
splitting it into training and testing sets, so we can do amazing thing with it and learn how to predict. And
Hmm.
then we have a next step that is choosing the right algorithm, right? Because this is the area where you come in again, uh, because experience really matters in this case. And some algorithms are great at handling small data sets, and others shine when you have millions of rows. Some are better to interpret something, and others are more for raw predictive power. So I'm not a data scientist, as I said earlier. You are my hero in this case. I understand the concepts. I can teach about it. I can discuss about it. I can come up with many ideas as I did in the past. Um, but Igor, can you give me a story behind those amazing numbers? How you have chosen algorithms in your projects? Because I know there are a bunch. I know, and we have algorithms and we have the model, right? The meal, as you explained to us. Can you help me to understand and maybe help our listeners to learn how to mitigate risks in choosing certain kinds of algorithms?
Yeah. So people who know me knows that I have a few hobbies. One of them, I do actually. My favorite hobby. Is my favorite hobby. I'm not sure if that makes sense. Out of my hobbies, that's my wife likes the most. It's making drinks. Not only making like classics drinks, but like creating my own recipes for drinks. And depending on the event, I might, and depending on the event and when it's the event, like what time of the year, the weather, the kind of thing, the people that are coming, how many of them, I might do different drinks, different recipes. Because if it is like in like Sunday morning, I might just do a classics like mimosa or something like that, or cosmopolitans, or rather than some more elaborate that I would do in an evening event and things like that. Sometimes it's during the week. I just want to do something quick rather than a weekend. So it's kind of the same. In machine learning, when we build a model, we just don't ask, does it work? We need to measure it. Remember, it's all math. Math, it's about measuring stuff. So we measure how well it works. So, and that's where evaluation comes in. And if you have to do it programmatically, you need to um, basically do those manually, kind of. So you need to compare what the model predicted, what was the reality, and then there was different ways to see how much the model missed, how much they unpredicted. What is the true positive rate, true negative rate? What is the different things? So, and I'll explain some of these things in a minute. Another thing, in order to choose a method, is like what question you're trying to answer and what problem you're trying to solve. Because sometimes the one with the best metrics is not the one you choose. So let me get to that. Let's say your prediction whether a patient will be readmitted to the hospital or not. So the module outputs a probability score for each patient. Let's say zero point 0.8, very likely to be readmitted, or zero point 0.2, not so likely. To see if the module is good, we check a few things. For example, accuracy of fit. So in regression tasks, like when you're predicting numbers, we use metrics like R squared, which call it the coefficient of determination, or mean square error, to see how close the predictions are to the real values. For example, the R square equals 0.9 means that the model explained 90% of the variation in the outcome. Pretty good.
Yeah.
So each algorithm or each kind of problem, we might choose a different measure of accuracy of fit.
Now, I
Another is
remember when we did those
Mhm.
projects, right? My colleagues, the amazing guys who are method magicians in mathematics, they
Mhm.
used R and RapidMiner in their early days in predicting things based on the historical numbers. And you could see the two lines, right? A red and a blue line, for example. And then when they were close together on top of each other, you knew you trained the model pretty good, right?
Yeah,
That's
yeah,
the
yes,
accuracy of
exactly.
fit, right?
Yes, and that's for like more like regression tasks. For
Hmm.
classification, we use metrics like precision, recall. There's F1 score, F1 macro, F1 macro, macro, micro, ROC, AUC. Those different ways to measure. Um, and then it will help you answer the questions like, is the model better catching true positives or at avoiding false alarms, things like that. And this is important because sometimes when using tools like click predict, let's say we use an F1 score to measure the modules, and based on that, click predict will say this is one of the best accuracy, based on F1 score. This is the best model, and we recommend you a module. It'll say this is the best one, but not necessarily that's the one you will pick because that's the best one predicting all cases. But let's say, you know what, I prefer higher true positives than higher true negatives. I want to focus on true positives. I want to aim to have the best true positives possible because it's a very, let's say, it's a very complicated disease you're predicting, or it's a very, let's say, churning high profile customer. So true positives are my goal. So you might go to another model that is good, but is not as good as the one overall as the one suggested, but has a better true positive rate, or sometimes a true negative. You know what? I want to make sure if I say someone is free of a disease, they actually free of the disease, because if I miss this, they might stop the treatment and the disease might come back like cancer. So then I will focus on the true negative rate. So you might choose differently than the suggestion. That's why understanding this concept is important. It's not just blindly choosing whatever is recommended to you. A lot of cases, what is recommended to you is the one I choose anyway, but that's the thing. And also knowing the algorithms. Let's say if ClickPredict recommended me a naive Bayes or random forest, I'll be skeptical about it. I said, really? You're not recommending a gradient type of a cat boost, a boosting or a gradient type of algorithm? Let me understand why. Maybe there's a problem in my data. Maybe I'm overfeeding. Maybe I'm underfeeding. So depending on that, so that's why it's important, and that's why it's important to look at our blog. Um,
Yeah, I
Let me
think
give
so.
you and another concept is generalization. You said that we split the data into training and test. Um, and there's cross validation, other concepts that I'm not going into details because people can go to our datavoyagers.net blog and read my articles where I explain all of these. And about this, I explain. There was one article about pre-processing where I explain like this cross-validation test training data set.
Yeah.
But basically, to one of the techniques to reduce the chances of overfeeding is, well, let me split my data set in two. I was one, instead of using all of the data from the past to train my module, I will use part of the data to train my module, and I will hide from the module the rest of the data. Once the module is trained, I will just deploy and execute the module without training, just execute the module ready to consumption, the deployed module on this new data set that I reserved, the validation or test data set, and see if the accuracy are the same or similar.
Yeah.
If it is not, if I see a decrease, I said, oh, if I had a decrease, I overfeed it, because it's pretty good in training. When I do provide new data, is not pretty good. So I catch that before before committing and putting in production and things like that. Let me give you a real example that happened to me. It's a big use case. Actually, pretty proud of it. Actually, it's still going project, but because we did like phase one, but we are we getting the funds to do phase two. Hopefully, we getting the funds to do phase two and three. But it's a healthcare project, hospital project, and we build a module to predict CLABSI. What is CLABSI? CLABSI is a hospital infection. So sometimes you go to a hospital and you put something we call a central line. So put a if people only listen, they're not seeing my hands showing, but they put a central line. So they put a line basically to access your heart or something. So they put a line, or maybe to give you medication stuff. They put a central line. If you Google a central line, you'll see some images, a little graphical, so not for the faint of heart. But anyway, if you put those, they can get infected, and it's pretty serious because if you get
Directly in your
infected,
veins. Yeah.
yeah, if you get infected, it's pretty serious. So predicting um, hospital infection, it's huge, but specifically that CLABSI that we work with. And first time we built it, actually we didn't build it. So first time someone who's not a data scientist tries to just an exercise, just click predict. This is all done in click predict and data flow to prepare the data split in training and testing, all data in so was done using no code approach. And then they did it and it got 98% accuracy. They said, great, I don't need data scientists. But then I said, hold on, let me take a look. When you look deeper, we realized infections were so rare that the model was just predicting no infection to everybody. Because the infection
Yeah.
only
Then you get
happens,
that high accuracy. Yeah.
yeah, because it only happened in 1% of the patients, if that many.
Mm.
So if it's like if you say nobody's gonna have it, you get it right. It's a model there's no algorithms. Just say I don't even look at you. I'll say you don't have it, because it's rare. You still get right 98%, 99% of the time. So the accuracy sometimes is misleading if you don't understand actual business because it's a rare condition. So when we switch the metrics to recall, precision, then we'll realize true positive, true negative rate. So the true positive rate was almost 0%. Because actually, I think it was 0%. There was some cases were being predicted as having the infection, but anyway, it was. So then the truth came out. The model was missing most of the actual infections. So we didn't need a module at all if we were doing that way. So we changed evaluation metrics, we used synthetic data, retrained. So then we built a module that caught far more real Class B cases than the initial one. So that's when the real data scientists say, hey, kids, no, you guys were unsupervised. Let us do the
Yep.
work. And then things worked.
Great. So then at the end, you were confident in the results. And then you deployed the model into real world, right? I think.
Yep.
Exactly.
Mm-hmm.
Yeah. So as we covered the projects, right? The steps in the workflow is defining the problem, collecting and preparing the data, splitting it into testing and training data sets, sometimes adding the validation set as well. That's the third set that you can use. Then we have to choose the algorithms. There's a big bunch of algorithms, as I understood. We have to train the model right, and then we have to evaluate the performance to find if we did our job well, right? And then we have to deploy it into the real world. And um, the real twist in our story here is that the workflow is actually not linear, right? It's iterative because you can train a model, find out it underperforms, you tweak it and you test it again, engineer some new features, maybe add more data or remove data, and refine the or redefine the problem entirely, and then you can continue. So machine learning is less like following a recipe and more like cooking a meal when you keep on tasting and adjusting it until it's right for your tasting, for your what you like, right? Uh, so great. And we have to manage and monitor and maintain things again, right? We did this complete project, and I know we already a long time underway, 1 hour and 11 minutes already at this moment, and I know there will be some minutes cut off during the moment that the video will be edited or the recording will be edited. But we have to talk about MLOps. Igor, guide
Yeah.
us through
So
the MLOps.
yeah, let's do it. So we talk about how to build a machine learning model, but here's the truth: building the model, training, that's the easy part. The real challenge begins when you try to use that module in the real world every single day at scale, and that's where MLOps comes in. So MLOps stands for Machine Learning Operations. And if that sounds familiar, it's because it borrows from the term DevOps, which is already well established. Which is a set of practices that made software development faster, more reliable, more scalable. So MLOps applies the same principles, but to machine learning modules. So think this way. Let's say you bake a cake at home. It might taste great. It's not so complicated. But if you have to serve that exact same cake to 1,000 people every single day, let's say you open a business. Oh, I'm a great cook. I'm open a restaurant. Oh, those are so different things. So different things. Like my wife, for example, she is a great cook. She went to culinary school. She's a chef. She hates when I say it because then it creates a lot of expectation. She's a chef. She studies. She understands. She goes to a restaurant. She tastes a dish, and she knows exactly every single ingredient, proportion. She comes back home and she can reproduce exactly the same. She's amazing. But then and she worked with like on that business. But I asked her, so why don't you open a restaurant? She said, no. I like this. The restaurant is a whole different thing. There's so many other things besides the cooking. The least you do when you open a restaurant is cook. So same here. You need to add like quality control. It's be a repeatable process, a way to make sure the recipe still works, even if the ingredients change. Let's say a supplier didn't provide the exact brains that you wanted. So that's exactly what MLOps does for machine learning models. So one of the biggest reasons MLOps exist is what we call drift. So data in the real world changes all the time. The world changes all the time. So customer behaviors shift, market evolves, seasonality kicks in, and suddenly the patterns your model learned 6 months ago no longer apply. Sometimes even because before you didn't have machine learning module, now you have a machine learning module, and people are behaving, business is performing differently, behaving differently because now you have the prediction piece. And so sometimes the change, it's a good thing because now, oh yeah, now we have more knowledge of the businesses because of the machine learning. So if you don't monitor that, you can end up trusting in a model that's quietly getting worse and worse over time. And that's why drift detection is so important. And this is not just theory. We actually measure we can do that. And there are two types of drifts that we can detect. Click Predict already has one of them, data, which I think is the most important one. Click Predict has data drift detection. And I do have an article called about data drifting, explaining what is data drifting. So basically, it alerts that when your incoming data feeding your model, it's starting to look different from the data it was trained on. The statistical properties are different. So then it will alert you. And then you know, oh, now reality is different. It's a different world. So I might need to retrain my module, create like version 2 of my module, which is a simple task, but you might want to do it. Now, there is another type of drift, which is model drift. So data drift monitors if the data changes. Model drift monitor if the accuracy of your model changes, like it starts to decline. So model drifting, it's another feature that Click Predict is adding real soon. I don't have a date. I don't work for Click, but I know it's real soon because it's in the early roadmap. So, and then when that's available, we'll have an article. That's a promise about that. But then, you will be able to see the actual performance of the module begins to decline. Let's say you're predicting customer churn within 6 months. 6 months pass, then you measure what actually happened, and then you see how much the module got it right, how much the module got it wrong. You monitor, and when it drops below a certain threshold, then you'll be alerted, and then you might need to retrain, you might need to reconsider what's going on. MLOps also covers version control because the modules are not static. You might retrain your modules every 6 months, for example. You might have module version 1.0 trained last year, module 1.1 trained with better features 6 months after, module 2.0 trained early with early new data. And if you don't track versions, it will be impossible to go back and explain why certain prediction was made a year ago. You need to trace back to the version of the module we had a year ago, which we do have already in Quick Predict, by the way. And there's deployment. So a module sitting on your laptop is nice. Some companies, and that's the beginning of machine learning was like there was one guy, a nerd, with the computer, big laptop, or not even a laptop, could be a computer, and then someone needs a prediction. Say, "Oh, can you run me a prediction?" And that person did it manually. No ML ops. It was like Igor ops. So then we have deployment. So a model that is sitting on a laptop is nice, but a model running inside the business systems, like in your Click Cloud, making predictions in real time is what creates real value. So ML ops ensures modules can move from experiment to deployment seamlessly and reliably. So without ML ops, machine learning often stays as a proof of concept, never implemented. A cool science project that doesn't survive the real world. But if you add ML ops, and especially with tools like Quick Predict, built-in detection, right in, machine learning becomes a living system, one that adapts, evolves, and stays useful long after the first training run.
Yeah, I know I had come up with some questions after we worked together on the document to prepare ourselves for this session. Um, and I think still that MLOps is very important nowadays, right? And it's related also to DevOps, right? But then in this case, it's on the machine learning elements. We talked a lot about bias, drift, and so on, and that is also covered in the amazing product of Click Predict. But I think there is one question that I really would like you to answer, and that is why is ML ops becoming so critical for organizations today?
Well, because building a model is only the first step. The real challenge is keeping it reliable in production. ML ops provides the processes and tools for you to monitor, retrain a model that is not being does not need to retrain is a model that is not being used.
It needs
Scale,
nursing, right? It needs
yeah,
nursing.
it needs as anything in software. Like it's if you do a cool dashboard that nobody uses, it could be the best dashboard in the history of dashboarding. It's
Yeah,
useless.
but if nobody
So
uses it,
yeah, it's so adoption is
yeah,
the main key for
yeah,
success. The same
yeah.
here, and this ops concept, it's for DevOps, for ML ops. Now we are now discussing LLM ops. So basically taking that and putting as part of the business, because the idea, and we call this ambient analysis or ambient machine learning, it's basically that ambient analysis or analytics is like the analytics, including AI, including all of that. It's part of the company's day-to-day operations. It's seamless. It's not like another task that you have to do. No, it's just part of your work, part of my work.
Yeah, exactly.
Sometimes people like Excel. Excel's part of the people's job for a lot of people. Replace that to something more governed,
Yeah.
and that's the whole idea. And ML ops for machine learning helps that happens.
But I think ops in any ways, looking back and refining things and taking care of it, maintaining it, scaling up, scaling down. Uh, I think those elements are very important in various elements in the industry, right? In project management, it's in software development, it's in everything, right? So um, we covered foundations of machine learning, the workflow, MLOps. Love that topic anyway, which keeps models alive and reliable in the real world. But there is one shift more happening, and that is truly changing who gets to use machine learning, and that's the rise of AutoML, right? Uh, so let's be honest, building the models that you did in the traditional ways with Python, with R, with RapidMiner, and so on. I believe there are many tools uh, to hard code algorithms. Um, but you know, there are just not that many data scientists around, and that's the issue. I remember I was talking to this company. They are from Belgium, and they told me in one of their sessions, because we became a partner of them in one of the former uh, organization that I worked for, and they said 80% of predictions is time series based. 80%, right?
Yes, yes. That's why I'm so excited about Click Predict adding time series real soon,
Yes,
because of
finally.
that.
Yeah,
Yep.
it really shines, right? AutoML, or automated machine learning, is designed to break a bottleneck for businesses. It takes the heavy lifting away from organization, the algorithm section, the parameter tuning, the cross validation. It automates it. It's automated. And suddenly we have Click Predict. And you told me, I believe 2 weeks ago when we start preparing for this session, even you can do this, Angelika. And I believe really that Click Predict shines in AutoML, and that you can explore your data with Click. And then when you see patterns, you have questions and you wonder what's going to happen next. Oh, with Click Predict, you have not to, you don't have to export the data, but you can move it into a data in the model, and then you have the results, right? Just in a few clicks. Can you help me with this a little bit, Igor? Because you are a firm user of Click Predict. I just started. I understand how it works, but man, that's powerful.
Yeah. So the whole idea, and by the way, it's interesting that Click Predict, um, it it was in the past another product, and Click acquired the company. It was Big Squid Kraken, and I used Big Squid, and so when Click acquired, I said, "Oh, that's great because I already know the tool." Of course, a lot of change, and I also use Data Robot, certifying Data Robot. I use Sage, AWS SageMaker. I use all of these tools. Um, they all follow the same concept of automated machine learning. And there's a lot of tasks in order to create a module, a machine learning module. Um, so there is the before you train the module. I mean, there's the data preparation. I'm not getting into the data preparation for machine learning, but let's say the data is ready to train. So there's a lot of pre-processing. You don't get like the raw data. There's a lot of pre-processing. I'll give you one example. You need to scale the data. Otherwise, some numbers will be considered more important just because they are bigger. Like if you compare your age to, I don't know, your um, it, salary. One is in the thousands, the other it's not in the thousands, is in the dozens. So the salary will be more important than age just because it's a larger number. So we have to scale. So there's a lot of preparation. So tools like that, they do all of those prior. And then you don't know what algorithm will be the best one. So there's some good candidates, usually like 6, 7, 8, like the most probable ones. So, but you don't know until you actually try it. So you need to train the algorithm in each one of those, and then you need to measure how well each one of those perform, compare them, pick one, and then once you have that, and then you will deploy that to production. There's all the ML ops kicking in. So imagine that you can do it all manually and have a project from data being ready to being deployed taking months, or you can use tools like this. So you
Yeah.
said that there's not so many good data scientists available,
Yeah.
especially a very rare unicorn is a data scientist that also knows the business piece. That is a data scientist that is not too academic,
Not too many.
but
No.
is business focused.
Yeah.
There are not too
But
many of those.
and we can
And
have a discussion about that as well in a future podcast, because
yeah, yeah,
do we believe in multidisciplinary teams, right?
absolutely.
Yeah.
That's the key. That's the key.
That's the key.
So how having, let's say you have one, two data scientists, or one, we call it citizen data scientist. Actually, I do a lot of training analysts to become citizen data scientists. So you're not a data scientist, but you know enough that you can perform most of the work, and maybe the data science will spend a couple of hours you just review and you exchanging ideas. How you do that? You do by using tools that eliminate the programming piece, because let's be honest, one, when I love Python, R, love it, but when I do have to write Python or R code, I'm not doing a data scientist work, I'm doing a programmer work. So if I replace that and automate those, and then I can focus my time. So one data scientist can produce as much as 10 other ones, just because the tools will save you some time. So
Yeah.
that's the key. That's why tools like that. If you
Yeah.
click predict, it's so easy paid. I mean, it's already included in the tool, so you don't have to pay extra, but it's so easy paid because if you have one customer that you accurately predict that is going to churn, and you, because you know that in advance, and you reverse that, the revenue that the customer is bringing, just one customer already pays for the whole thing in a
Exactly.
lot of
And
cases.
that is why it's such an important step forward.
So basically, the cost for click predict, I'll say it is negative, because
Yeah.
the benefit, if you do
Exactly.
right, the benefit,
Yeah.
overcomes, like the return on investment is so great,
Yeah.
because then you're
Yeah. And even
understanding
I
the
am
business.
starting to understand it, right? I hope to become an amateur citizen data scientist who understands it. If you understand it a little bit, you can
Hmm.
actually explain it to others, and that's the cool
Yeah.
thing. So,
And
Igor, I think we have to end
if
up,
you people
right?
are interested,
Yeah.
send me a
Reach
message.
out
We
to
can
Igor.
talk. Reach out to me. We can discuss even doing the work, training your team. It's a 3-day training. It's not only
Yeah.
the machine learning piece, is is the statistical piece and the other things and quick answers and all of that. So yeah, reach out.
Yeah, cool. So, Igor, I truly believe we have to end up now. We are already uh, 1.5 hours on the road, and we are still not finished in this
Let's do it.
discussion. So, thanks, Igor, for being here today. Can you close up, please?
Absolutely. So, as we've seen today, machine learning is no longer locked in the lab. From understanding the basics to making models work in production with ML ops, and now with AutoML technologies like Click Predict, machine learning is more accessible than has ever been. And here was one people to remember: the machine learning is not something to fight, and that's a reference to Race Against the Machine. Yeah, it's not a race against the machine learning. It's not about rage against, it's about rising with it. So the machine brings the power of scale and prediction, but it's up to us humans. There's always need to be the human in the loop to bring meaning, judgment, and action. Folks, that has been the Data Voyagers podcast. I am Igor Alcantara. This is Angelika Klidas. Thanks for listening, and always keep exploring.